Morning again. So I'm going to create a video presenting and introducing series parallel combination circuits. So this will not be on the midterm. Still making videos because of the snowstorm. We just need to keep moving forward as a class, so I hope people are watching these videos because we still need to cover the class materials to get you prepared for future classes. There's a certain level of expectation when you move on in the electronics program. Like when you move on to AC, it's expected that you learned everything that you were supposed to learn in DC. So that's important. Another entry slide. I'm not going to sit here for too long. I'm hoping everybody gets this by now. Series parallel combination circuits. To go back to series, we have series circuits. Voltage drops add to equal total voltage. And you can do that by using Ohm's law, and adding up the resistances and putting that in the denominator and putting source voltage in the numerator. That will give you total resistance in a purely series circuit. From there, you can use Ohm's law again and just multiply the current by the individual resistor values for individual voltage drops. Just remember that all components share the same current in a purely series circuit. It's kind of opposite in parallel. They all share the same voltage. All resistors share the same voltage, but they have the current divides inversely proportional to the resistor values. So when you start dealing with series parallel combinations, and this one is R1 parallel R2, and that combination is in series with R3 parallel R4. And next. So this is just the last slide shrunk. If you can't see it very well, just go backwards a little bit in the video and just draw the last schematic, and that's what this one is. And so it looks like this. Hold on. R1 parallel R2, and that parallel combination is added to R3 parallel R4. So the first number is going to be R1 parallel R2. I'll do product over sum for that. Comes out this whole thing comes out to equal 71.4 ohms, and this whole part, product over sum, comes out to 127.3 ohms, and I'm rounding here a little bit, but that's fine. So next, we'll create a little chart like Sharka does over here. We're going to find our I total. Actually, let's find our R total first. Add them up. Let's put that on top. R total equals those two numbers added together, 198.7 ohms. Make sure you're always including your units in your numbers. So then for the next, we have VT equals 24 volts. So if we were to divide 24 volts by our R total, we would get our I total, which is I total equals 120.8 milliamps. Next, we can just, there's a couple different ways to do this, but, so, which way do I want to do it? Okay, so the first time, I will do it by, so I'll calculate the voltage drops on R1 and R2 by, first calculating their current, which the 120.8 milliamps will split. So we have I1 and we have I2. So for those calculations, we just do their branch total as our total, and this, so we have 120 milliamps times 71.4 divided by, we'll do 100 first, 100 ohms. Put that in the calculator really quick. 120. So I got 86. We'll just round down on this one. So we'll just call it 86 milliamps. So I1 equals 86 milliamps. We know the remainder of that 120 is going to be at I2. So 120.8 minus 86.25 equals 34.55 milliamps I2. So that's how we would, so from there you can take those individual branch currents and calculate the voltage drops, because, well, they're going to have the same voltage drops, but they're not going to have source voltage is the thing here. So essentially, I'm going to draw on this picture a little bit. Imagine that these simplify to one resistor as far as voltage drops are concerned. They will have the same voltage drop, but it will not be source voltage. It'll be like, this will end up being like two series resistors when it comes to voltage drops. So next we're going to do our I3 equals, I should probably be doing IR3 and IR1, IR2, but we'll just keep on doing what we're doing. And so we do that, we will still have the 120 milliamps going through the total. The total current will still be going through the two branch resistors. So we do 100, this time we put 127.3 ohms on top, because that is the branch parallel combination, our total, and then our total for the branch. So then put 200 on bottom, got 120 times 127.3 divided by 200. So we have, I did IR4, so 76.4 milliamps, and our IR3 will be, or I3 will be the remainder of that. So 120 minus 76. So we have 43.6 milliamps. So you can take any of those currents and multiply it by the resistor, and it will give you what the voltage drops are. So we'll do it off two of them. We don't have enough space to really do all four. So if we were to do, let's do IR1 or I1 first. If we multiply that IR1 by 100 ohms, we get 8.6 volts, and we know that it'll be the same for I2 then, because they're parallel. So I'm not even going to put this one in the calculator, because I didn't put the last one in the calculator, but you know that 86 milliamps times 100 ohms comes out to 8.6 volts. And if it doesn't, I'm going to have to redo this video. So then, naked numbers, got to put the V there. So then we got the IR4, which IR3 will have the same voltage drop, but IR4, well, we know that it'll be the remainder of the 24 volts, so if we just subtract 24 minus 8.6, it'll be 15.4, but I'll still calculate it. So IR4 is 76.4 times 200 ohms equals, let's verify, 76.4, use the negative third, times 200 ohms. Yeah, it's just a rounding issue. It's more like I came out to 15.3, but it's just an issue of rounding. So, hope you're all following me so far. It really, in the coming weeks, it's only going to get a little bit more advanced. So, this will not be on the midterm, by the way. So just keep racking up the points. If you struggle with some of the later stuff, just absorb as much as you can. This snowstorm is really throwing a lot of things off. So here's another example. Could do this. I'm kind of on the fence. It's a little more advanced than where I think we're at as a class. So I'll do it, and if you guys, you can always rewatch the video as many times as needed, because you're going to need to learn this stuff, so I need to present it. So first thing we're going to do is add up our, well, I'm going to write out what I see here. So we have R1 plus, going to need a double bracket, plus, yeah, double bracket, R2 parallel. So now we begin. We do R, whoops, not 5. R1 plus, which means in series with, we're going to need a double bracket, R2, which is in parallel with, this is our second bracket, R3, it's in series with R4, and both brackets, whoops, that's kind of ugly. Okay, so that's what we're looking at here. So, first thing I'm going to do is I'm going to figure out the parallel combination. So what you do is you'll add these two together, and you'll put that in parallel with R2. So 6 series combination, the series combination of R3 and R4 in parallel with R2 is 6 times 3 divided by 9 equals 2. So this whole part is 2 ohms. I'll write it 2 ohms beneath that. And we know R1 is 4 ohms, so our R total equals 6 ohms. So then our I total will be, no, not even right, V total, because we can see it there, it's 20. Our I total will be 20 divided by 6, which is 3.33 amps. Now this is amps, not milliamps, because we have very low resistance. This is not K ohms. So we're at 3.33 amps. And then from there, we know that IR1, the total of the current will be going through resistor 1. The total current has to go through resistor 1, because the total current has to get back to the voltage source. And there's only one path to get to that parallel network. So our IR1 equals 3.33 amps. From there, I'm going to do current divider. which is 3 point, and I'm solving for IR2 now. 3.33 amps times 2/3 of that. 2/3 of 3.33 equals 2.22 amps. And IR3, well, IR3 and IR4 will have the remainder, and we know that there's only one path for that 1.11 milliamp to go, so they'll both have 1.1. So we'll do IR3 equals 1.1. Oops, not 1.3. 1.11 amp, and as does IR4 equals 1.11 amps. Oh my god, my cat's being so cute on my lap. Anyway, side note. So next we can, from there we got all our currents, so we can multiply and get the voltage drops. So not for IT, for IR1, 3.33 amps times 4 ohms. So we'll bring that times 4 equals 13.33 volts. So next we have IR2 times 3 ohms. So we have 2.22 times 3 equals 6.66 volts. And IR4, just do 1.11 times 2 equals this pen is awful. Equals 2.22 volts. And we know the remainder will be at IR3. So we'll write up here IR3 equals, that was 4 ohms, 1.11 amp times 4 ohms equals the 4.44. Oops, dropped my pen. That's what I get for talking bad about it. It's rebelling. So what you'll notice is IR3 and IR4 add up to equal, what they add up to equal? IR2, because they're in parallel with IR2. So that series combination, they'll have individual voltage drops, but they'll have the same current. So this one's beyond where we are right now, but we're going to have to get to this. If you have to watch the video a couple times, do so after the midterm. I'm just loading it now for people that are already prepared for the midterm, because I don't want to slow people up that are ready to move on. But if you need any help with stuff on that study guide, feel free to email me. I loaded the study guide onto Canvas in week 7 modules. And looks like all our values are right. Woohoo!